Okay, good morning, everybody. Welcome to this session. First of all, I would like to congratulate TBSI for launching such a successful event today. And we have a big team of CTU students and also colleagues from Hong Kong who are joining this session today. In this 50 minutes, the first 30 minutes will be delivered by me. I will spend around 30 minutes to talk about the topic today is about secure RISC-V processor for AIoT devices. And then we have about 15 minutes, our two students, Jerry and Vince, they are both a third-year undergraduate student who are doing summer internship under the supervision with Dr. Tan and also Lizzie and also student in TBSI. So in my talk, I'm going to cover 4 different areas. So you may find out there are lots of information in this talk. Number 1 is about security. So we are going to talk a lot about security. How are we going to enhance the RISC-V security aspect? And second one, we are going to talk about the process architecture. And today we already learned a lot from all the speakers today about all the exciting upcoming activities in RISC-V. So I'm not to talk too much on that, only talk about our augmentation and our research to secure RISC-V. This is our main focus. And then the third one we're going to talk a lot is about the IoT, Internet of Things. So we are very fortunate to collaborate with support from Hong Kong industry. So we're able to deploy our chips in the IoT environment and also doing the production line in the sector. And finally, the last element in my talk is about AI. So we're going to talk about how we do AI and also enhance these IoT devices. So these are the 4 main areas in my talk today. To start with, I would like to first introduce my research team. So this is our research team called CTU Architecture Lab for Arithmetic and Security that was founded 10 years ago. So we have about 20 years history to work on security related areas. So at the moment, we have about 30 people in our team, including postdoc, PhD, master student, and some undergraduate student, including Jerry and Vince. And 12 of our PhD students already graduated. So they all, half of them work in industry and academic. Many of them work as a faculty at the moment. So this year, we actually have a 3 mainland students doing a PhD in Hong Kong. So this is only a picture showing our team. So only one of the team in Hong Kong. As you can see, City University has been ranked the most international university in the world by QS ranking. By the Times ranking. So you can see our team consists of many different kind of nationality students in our team. So we have a very diversified team in Hong Kong. So now I go to talk about the motivation and challenges that we are facing in this research area. So we will talk about the 3 different IoT applications, including the aero hydroponic agriculture system. So in the agriculture sector, how do we apply the IoT devices in this setting? Second one, we'll talk about the energy saving for smart city, for smart building, smart office. How can we reduce the energy? This is the second area. The third one is what we call the LoRaWAN-based camera monitoring system. So I will have a few slides to talk about the application side for the IoT. Second one, we are going to talk about the IoT security. So we will focus on 2 areas. One is called the secure RISC-V platform, which is our topic for today. And also we have a lot of experience to work on the cryptographic hardware design, including the 2 areas that we want to talk today is called the lightweight crypto and also post-quantum crypto, because we know that the quantum computers coming along, and if that happens, all the existing crypto standard will be broken. So how can we secure our chips to defend the upcoming attacks? And final one, because we're talking about the AIoT devices, we want to have such a tiny devices with the RISC-V enabled, and how can we embed our AI applications inside the chipset? So this is the research that we are actively working on at the moment. So next one, I will talk about the IoT application. And we can see that IoT is an area that we apply in smart city, smart home, healthcare, manufacturing, and many different domains. So we really see a lot of a problem in this area because of the booming and the increase of the IoT market. The number of devices has been doubling or tripling over the years. And however, the problem with this is the power efficiency and also the lightweight features will sacrifice the performance. and we see a lot of breaches, a lot of security problem. So how can we divide the chip into certain area with secure region and also normal region? How can we do it? And this is again, we don't want to sacrifice the lightweight features, because if we are putting a lot of design into the chip, we lose these lightweight features. So the idea behind is with more data, we do more analytics, and we can do better decisions. So here is the first scenario that we already have the prototype in Hong Kong. We recently submitted a paper to IEEE Transitions to describe this scenario. So you can see at the upper is the aeroponic crops like the veggies, and the bottom part is the hydroponic veggies. So you can see we are putting the two systems together, and we are putting a lot of IoT devices to do all these different sensors. And imagine if this is a scenario, we are putting the RISC-V processor in this kind of setting, and we want to secure this. And here is the overall picture. We call it AHAS. This is the AHAS. So we're having the water pump. We have all these different sensors. At the moment, we're using some chips. We're trying to put together with our RISC-V the chip into the system. Second one, we call it the system called the BLESS. Okay, so this is the system. We can see this is the office setting. We are installing the IoT devices, and our goal is to control these curtains, the lights, and air conditioning with a smart algorithm. We're able to minimize the power efficiency. The third application we want to introduce today is called the LoRaWAN-based camera monitoring system. So you can see these are the long-range Wi-Fi camera node, and we want to connect them with the system. And given they have a long range and they want to reduce the power efficiency, but again, they have all these what we call the access policies. For example, on average, 30-second uplink of the air for every 24 hours. So the time for the transmission is very limited. So in that kind of IoT scenario, how can we ensure the data is transferred? And also we propose our new algorithm. For example, this is what we call the CIRA, okay, the compressed image and recovery algorithm. This is the JPEG format. This is our CIRA. So we propose our own image algorithm, and we can restore the image. This is the original image. And by having the recovery algorithm, we're able to, using this long-range Wi-Fi, and we're able to do the compression. So here are the few applications that we start with. And now we can see we want to pose two important challenges that we are facing. Number one is how do we secure all these IoT devices? We see a lot of attack is happening, and this is the first question that we want to address. Second question we want to address today is how do we deploy all these deep learning algorithm nowadays into all these tiny devices equipped with the RISC-V processors. As you can see, the model is blooming because we're getting more and more data, and the challenge is how do we compress the model into these devices. So how do we do the inference on the edges? So at that edge, tiny resources with only a very tiny memory, how can we do the inference? Because we are not going to load the whole AI model into the chip. So we want to make edge-based inference feasible. Okay, so we are taking a step and work on this area. Now we're going to step into the second part, which is the security part. We're going to introduce our research team, the current status. First of all, we want to highlight cryptography and security. They are not the same thing, but they are working in parallel. They want to support each other. So cryptography is the algorithm, the mathematical proof to support the crypto standard. So security is built on top of all these crypto algorithm, and we want to enhance. That's why when we are talking about RISC-V, secure RISC-V, we are embedding all these crypto component into the RISC-V processor. So we want to mention that. So here is the idea. We want to protect the device, and in particular, when we want to talk about a CPU, there's a component we call the root of trust, RIOS. So that is the fundamental computing devices. So that's where we call it usually where the key comes from. And afterwards, you have got these different layers. For example, you've got the hypervisor layer, the OS layer, just like the RIOS the student they're doing. For example, how do you do the memory protection? So all these cache coherent is all in these layers. And then today, when you talk about the ARM processor, there's what we call the trust zone. So you can see there's a normal world, there's a secure world, and how do you transfer the data and ensure the data is being transmitted and not monitored at the right time. So the main challenge today when we talk about we want to secure the RISC-V for IoT devices, the real challenge behind is this. We need to support non-lightweight algorithms. So they are quite heavy-weighted. So the solution is we want to have some lightweight coprocessor approach and also this cryptographic coprocessor. And also you want to reduce the runtime for this processor. So that's why you may want to keep some secret inside the chip. So that's why if you look at the IoT devices, it's quite different from we are looking at the PC and also the mobile devices. So again, they're very tiny devices. The resources is very limited. So here is what we want to again highlight the figure that you've seen earlier. So this is the normal region. This is a secure region. And inside the secure region, we've got the cryptographic processor we just mentioned, and there's a cryptographic primitive. And inside, there's a key generator. We will spend a bit more time to talk about this key generator. And then you've got the transparent engine, because we are convinced that we need to ensure the safety of the chip. And afterwards, there will be a region, what we call the secure memory. So you can see even that the chip has been compromised, has been broken, and we can still keep the data inside safe. So how can we achieve that? So when we talk about the root of trust, we start from the fundamental building block, and that's inside, let's say the chip is the flip-flop, the lux, and so on. So here is a typical, what we get the randomness. Where do they come from? So imagine this is a typical ring oscillator. So there's a ring, and then you get all this data keep on switching. And later on, you do some sampling, you get the data, and then eventually you've got the final bit. And all this bit, you have some sampling. You want to collect the data. We have this what we call the processor, and eventually you get some random bit. And we are able to observe the waveform and capture all the different glitches and all this uncertainty, what we call the metadata. So this is what we call the free running ring oscillator. And in our recent publications and also our PhD graduate, so we propose the stage of running this ring oscillator and appear to be pretty nice. So that's why we developed our own true random number generator, which is one of the state-of-the-art design. And the result is passing the NIST test and also DIA test, which is this up-to-date to showing this is a true random data. Second one, I'm going to talk today after this root of trust, we have this component. Next one, I'm going to introduce to the audience today is the cryptographic competition by NIST, which is the up-to-date de facto standard in the industry. So there has been two ongoing crypto like a competition in the world. There was like a SHA competition before. There's some other competition before. But if you look at 2016, the PQC competition, and up to today is still up and running. So no final list has been selected. And the second one is very suitable for what we are looking at is what we call the lightweight crypto, and it started a little bit later. So at the moment, NIST announced 15 third round candidate. It's already the third round. And then the NIST also announced 32, the second round candidate for the LWC. One is for PQC. So I want to go a little bit further on that. So PQC, because in 1994, Peter Shaw showed there's a paper published and saying, okay, if this is going to break this integer factorization and also discrete logarithmic problem, then the current crypto standard will be broken. So that's why people are looking into this kind of problem at the moment. So that's why if you look at the up-to-date PQC standards, so there are so many different standards up and running. They're all by the mathematicians and cryptographers. And you can see we can actually divide the algorithm into different like modulus operation, the Montgomery reduction, some kind of multiplication and others. So how do we map this kind of instruction into the RISC-V processor is actually a big challenge. It's a big PhD topic. And that's why today when we ask the question with Mark, we want to see how we can actually connect our research to the RISC-V Foundation and also the international community. And that is very interesting. And second one, we are talking about the LWC. The LWC is a lightweight crypto. And if you look at here, this is again, the workshop, the competition is still up and running. LWC is looking at the lightweight and very resources constrained devices. And we are seeing there are a lot more devices happening in the whole world. And again, this is a very pressing research area. We want to connect and also talk to the researcher in the RISC-V community and see how we can secure every single component inside the RISC-V processor, because and this is going to be what we see in the next wave. Now, at the moment, if you look at these 32 candidates, 2 of them, they claim to be providing quantum resistance, and the other they are not. And I'm going to talk a little bit more on these 2. One is called the SCON. If you look at the data path, it will be very typical crypto standard, including initialization. You process your data, and there will be some plain text stage, and finally you process your data in the plain text mode. So we don't talk about the algorithm at this stage, but if you look at the standard itself, they will be involving encryption standard, hashing standard, and they are the winning candidate for the previous competition called the CISA. So CISA has been done, and they have been chosen as the best one. And the structure itself is very similar to the standard called the SHA-3 standard. And they have got a very low memory footprint, and they want to be like a quantum resistant for 160 bit. So this is what we are looking at the crypto standard. Second one is called the Saturni. Okay, this is again focusing on the encryption standard and also allowing hashing. If you look at it, it's like a tensor. It's actually a tensor. So it's very similar to all these AES standard. You keep on switching the data, processing it. And the real question behind is in RISC-V, in the processor, how do we create the right instruction to facilitate this kind of computation? And that is very interesting for us. So NIST also provide this kind of 5 different security standards, including level 1 to level 5, and they want to say, okay, how do you use an exhaustive search to break the AES? How do you use a collision search to break the SHA? And this is what we try to benchmark if we're able to propose our new standard and we're able to define in this level. For example, we can say this is going to be the RISC-V crypto defended like a standard for such a NIST security standard. And I think that would be very interesting if there's a paper to work on that, and I think it will be amazing. When we talk about putting the IP into the RISC-V, there are different ways. For example, one approach is that you have a coprocessor, you want to connect with the bus, and obviously there's an overhead. And the second one we're going to show you later on is that we want to have a micro-architectural changes. So we're able to put our instruction together with the RISC-V processor. So here is the idea. If you look at one approach is talking about is you've got a bus, you create your secure IP, and then you connect to the bus. And through different components, you are able to talk to the RISC-V processor, and then you achieve your ultimate goal. This is one approach. And the second approach is this. So we are taking a micro-architectural changes. So here is the 5-stage pipeline. You've got the fetch, decode, execution, memory, and write-back stages. And we are looking into the memory component. So we are able to provide our, let's say this is the keygen instruction. So we are able to connect our ring oscillator, we generate the key, and then we put together and augmented the research in this community. So we have a very smart PhD graduate, Dr. Liu Yao. So it's been putting a few years of work in this, and in our team, the chip that we name ourselves is called the RISC-V. So we hope more people are using it. So we want to collaborate with more researchers in Shenzhen, in Taiwan, and also the rest of the world. So we're able to create the compilation framework, and we want to develop this along the line. And again, so the tools we use is at that moment, so we are using different kind of a RISC-V. For example, we use a rocket. Later on, we will talk about is currently we're using Popino. We are using different kind of RISC-V for our research. And our goal is very clear. We want to enable and equip and make the RISC-V processor better and also more secure. That's our goal. And we believe this is so important. And at the moment, if you look at the system, previously we talked about the LoRa connectivity, right? So how do you have a RISC-V chip, and then you talk to the different part of the world, and let's say you're sending the image over the long-range Wi-Fi, and here is the Wi-Fi the LoRa radio frequency transceiver. So the tools that we're using, the chip we're using is called Symantec. This chip. So we're able to connect. This is the antenna. You have a kind of processing, and then you through the SPI, you talk to the RISC-V. So we are actually developing a system. We are not just looking at the research at the processor level, because we want to provide a solution for the industry for better mankind. So here is the brief like an overview of our research. Because of the time limit, we are not going to talk too much in detail, but we hope we could share more with you later on. So here is we've got the backend. This is the server, okay, and then we through the MQTT protocol, we talk to the LoRa gateway, and through the gateway, we are able to send the data to the LoRa transceiver. And this transceiver, you can see this is the edges devices. So we've got the tiny, at the moment, we're using FPGA, and later on, we hope we could fabricate the chip, and then we can put it into a production line. And then we've got this RISC-V core with the secure extension and also the security component. So at this moment, we want to ensure the whole stack is secure. So that's why in the protocol level, we need to do modification. And the architecture level, we need to do modification in the ISA, at the bus, and also the memory. And again, we want to start from the RIOS, the root of trust. And then later on, we want to provide the right cryptology to enable our whole stack. So at the moment, you can see this is the tiny devices with the LoRa. This is the antenna. This is a tiny FPGA. So we're going to put together, have a different stage of prototyping. So this is the rough prototyping. And at the moment, we are actually designing our board. Okay, so we are getting the FPGA specification, and then we're doing the chip diagram. We are trying to develop our own chip, and then we put even all the antenna in one single chip, and then we're able to put the RISC-V inside the FPGA, and then that is the SRISC-V. Okay, so at the moment, some exciting progress that we would like to share in this nice RISC-V bootcamp today is, so at the moment, the communication channel, we are setting this up, and also the LoRa A-loT. So we have a different kind of, initially we're using ARM, and later on we are switching to the Rocket RISC-V. At the moment, we're looking into the lightweight, the Popino chip with the SPI, and we talk to the chip, and we try to build the A-loT. And also the firmware, there are lots of challenges that we're actually facing, because when we talk about building a system, so to get it to work and see the result, especially everybody can imagine how much engineering work is involved in here. I guess I only have 5 to 10 more minutes, so I'm going to quickly introduce the second part, which is the AI component, because I promised that I'm going to share 4 components, which is security, RISC-V, and AI component, and also IoT. So the remaining part is the AI component. So our scenario is that we want to have a system. Okay, in this system, all the tiny nodes, they're empowered with a RISC-V, and again, they're very smart. Okay, they're intelligent. So how you can actually make the edge devices able to infer by themselves. So we are able to propose some what we call the compact CNN model. So we want to do the binary CNN. So the tiny data put into the chip has been really compressed, including the bit width, including the model, the number of parameters. We want to optimize these 2 parameters. So that's why the first thing we want to share is in a typical neural network, the CNN model, you will find out they are talking about 32-bit. The data width is like a full precision or double precision. It doesn't matter. As long as the data has been calculated, as long as the model has been trained. So here you can see the input we're talking about is a 32-bit of the weight. So we're able to compress, okay, with what we call the weight binarization. So the data will become 1 bit. And then later on, in order to have a CNN, you've got multiple layers. So layer 1, you squeeze the data into one, this is what we call the 1 single bit. And this bit will be fed into the next level for further computations. So that's why when we talk about this kind of devices, you can see in the training part, we talk about the training is a pure software. This is a full precision. But later on, when we talk about the hardware side, this part is talking about the binary data bit. So it's compressed. So this is what we call the hardware-software co-design as a system overview. And later on, because our team in Hong Kong, we're focusing on architectural design. So that's why you can see we focus on how do you use the right multiplier, how do you design the right adder tree, and this is the accumulator and also register. So we have our own architecture and put into the FPGA for realization. This is showing only one of the layer. This is one of the layer. Eventually, if you look at the AI model, they will be having different network structures. For example, you want to have the stream computation, okay, and you want to have a different structure in this AI model. So people, they're looking into how do we get the optimized structure for this AI model. So that's why, because of the different computational module, usually in our hardware computation, as many of us are computer architects, so we know you will generate a lot of bubble in your pipeline. So in our research, we also minimize this kind of bubble for this binary CNN computation. So the tools, the platform that we want to compare is the VGG small, which is a very typical AI model, and the other one is called the SqueezeNet model. So here is a very brief result that we want to show to you today. For the full precision, the weight, okay, internal weight, and also A stands for the activation. So the activation activate the next layer. So this is a 32-bit and 32-bit. And the word we are using, this is talking about 1 and 2-bit. So you can see our model, we're talking about the inference accuracy is pretty much very similar to the full precision that we are able to achieve. This is talk about 86 and also 87%, so which is pretty high. However, more importantly, what we really like to share today is that for the ideal CNN, because you heard about it, we're talking about from 32-bit squeeze to 1 single bit. So apparently, we want to have a 32 times compression ratio. We want to compress the model to make it much smaller so that we can fit into the IoT devices. We call it the AIoT devices. So you can see the model we are squeezing from like a 5 megabyte to only 0.16 megabytes. So now this is nice because you talk about these tiny devices, you only have a very small memory space to hold your data so that this chip can do the recognition, can do the inference. Hey, you know, this is David, this is Dr. Tan, for example. You want to have such a compression. And then I'm going to share a bit more for our results. So we're able to put our design in FPGA, GPU, and also CPU. And our results show that the LNG efficiency for the FPGA is the best. So we're able to see this is the result as compared to the CPU and GPU. And we use silent toolset using the high-level sequences tools and also the sync. Okay, the sync is the FPGA that we are using. And we also compare our work with the up-to-date research community colleagues, so we can see our energy efficiency is the best. But more importantly, as we just mentioned, we're able to have the network feasibility, including the structural changes, including the operation level changes. So our design is more flexible. Final part, I would like to quickly go over the final part. The idea behind for this one is called the network pruning. So what does it mean? If you look at this fully connected network, so you can see a lot of node is connected. So this is again, of course, you can get a good result, very accurate. But again, you need to process a lot of data. So imagine this is an IoT device running the RISC-V. You want to minimize the computation in here. So how can we minimize all these nodes is the key point. So our approach is we have a training set. We want to keep on pruning. We want to reduce the number of the parameters. So we have a way to do it analytically. So we have an algorithm. We want to minimize it. So due to the time, I just go over to the highlight. Okay, so we're able to create what we call the trainable pruning threshold. So we are adding new parameter in the training process. So we are having a new parameter. For example, in this pipeline, so this is the layer. So what we call is we create a new parameter to make it a mask layer. So eventually, when we are talking about the training process, we're able to create a new parameter so that we can optimize and reduce the number of internal nodes. So this is our approach. All right, I guess I can just go over to the result. I think result will be more interesting. Okay, this is the idea. Okay, this is the idea. So we have a different what we call the NIST architecture. So different architecture. When we talk about the dense, this is the dense layer, fully connected. And also we want to compress it to the one we want. And you can see the one. Finally, we compress it to only 2% of the original design. So that means over 90% of the internal has been gone. However, the accuracy, we can still achieve over 90%. So this is, again, very, very good. So that's why if we compare our work with other sparse network, so you can see the result, we are still as comparative to the other work. And the model remaining, okay, this is the model remaining. So the final model remaining talking about 20% to 10%. So we're able to achieve this goal. And so finally, I guess everybody will be interested to know more about what our work is doing at this stage. So our goal is here. So we want to have this new network design for more parameter and handling more different model. So we want to see how we can create a hardware-friendly network structure. So this is our current research goal, together combined with the research with the RISC-V community. So we have proposed two important work. One is called the binarization to accelerate the CNN. And also we have this very efficient network pruning algorithm to minimize the internal parameters. So at the moment, we are trying to integrate with a new PhD student this year. So we are working to combine the two together in one framework. And we hope to open this work into the community, just like what RISC-V is doing. And we hope this part can benefit the research community. So here is the idea. So we want to start from the high level, the AI network model, and then we are able to compress the model to have a fewer nodes. And also this is talk about the quantization. Okay, so you want to quantize from 32-bit to 102-bit. So we want to compress it. And eventually we're able to design our dedicated hardware. And this is connected to the RISC-V work. And we make it as a big piece of work. So with that, I want to summarize my sharing today. Number one is we talk about different IoT applications. We hope that will be interesting to you. And we focus on two important components. One is the IoT security. We talk about the lightweight crypto and also post-quantum crypto. And finally, we talk about the edge-based inference. And we believe this is going to be very important in the IoT, in particular, also connected to the RISC-V. In particular, when you heard today, there's a speaker in the beginning, the industry leader mentioned in the 5 years' time, the processor, the market will be dominated by the RISC-V. And I believe that will happen as well. So finally, I would like to show some recent publications of our research team. In particular, the bold one is a 3 PhD graduate in our team focusing on this area. And I would like to give our appreciation to the CPU team, security team, and IoT research team, and with all the team members involved for the hard work, and also TBSI RIOS for the opportunity to work with our students together. And we receive funding from Hong Kong government and also the industry support from Dr. Alan Lam Central Company. And just 10 more seconds, I want to highlight on top of this project that we're working on at the moment. So we also have a big project led by Professor Yang Hong. So he's the chair professor in my department. So this is called the Center of Intelligent Multi-Dimension Data Analysis. And I myself is one of the members in this team. So this is the project with Oxford and also the Alan Turing Institute. So we are targeting to design something like a TPU, Google TPU. So we want to accelerate this process, and that will involve a lot of exciting research. And we hope to collaborate with colleagues in the region. So this project is talking about 200 million Hong Kong dollar, and starting from this year for 5 years, subject to the second 5 year. So with that, I'll be happy to take any questions with the audience. Thank you. 谢谢大家希望我的内容大家可以不会觉得太多哈，谢谢。
Thank you, Dr. Ray.
Welcome. I hope you like my talk. Thank you.
Yeah, 看大家有没有什么问题，我们可以 take 一些 question， 然后接下来是 Ray 的学生，所以我们也可以一起 Q&A， 或者看大家现在有什么问题。
我看到有一个问题，有朋友问怎么可以参加我的组。Yeah, thank you for your question. I think it's very easy. So you just Google CTU SGS, okay, and then you will find the application procedure to join CTU. And just remember to apply to the EE department. We welcome you to join us. Thank you.
OK， 那看一下大家还有没有什么问题。如果没有的话，我们就进到下一个 session 由学生的 discussion 和 present。
谢谢 Lizzy。
谢谢 Ray。
Nice to meet you, everyone. I'm Vince, and this is Sherry from the University of Hong Kong. We are both extremely honored to be here today to share our experience in the RISC-V related work. In order to get you guys more familiar with our university, let's take a look at the data about CTU in 2020. According to the US News Best Global Universities Ranking 2020, our department, the Electrical and Electronic Engineering, ranks the first in Hong Kong and the 15th all over the world. You can visit our department through the link below and find more information. Many thanks to Dr. Ray, who has been bridging a tight connection between the RIOS Lab and us. He is the author of more than 170 journal and conference papers. He is also the research group leader of the A-loT team, who has just given a brilliant speech. He holds the position of the chairman of Hong Kong STEM Education Alliance and the honors secretary of IEEE Hong Kong section. Above that, he plays an essential role in our department, being the director of the CTU Apps Lab, the associate program leader of the CDE department. In addition, he is also awarded for his excellent teaching in the year 2012 and year 2020. Next, please allow me to introduce our excellent research team, CALUS, CPU Architecture Lab of Arithmetic and Security. The goal of our team is to implement security-aware system containing time area, performance security, and energy cost trade-offs. We have a wide range of interests, including security-aware hardware design, robust data path design, and embedded system design, etc. So please find more details through the link about our talented team members. We cherish the opportunity to collaborate with the Tsinghua Berkeley Shenzhen Institute. Established in 2014, the Institute has been promoting global research and first-class education to more students. To know more about it, you may visit through the link. Our original plan was to conduct experiments in the RIOS Lab in Shenzhen. However, due to the outbreak of the coronavirus, the work and meeting have all been altered to the online form. RIOS Lab is dedicated in the development of the open source RISC-V chip, and we are very fortunate to accept the guide from Dr. Tan. Dr. Zhang Xitan is the co-director of the RIOS Lab and the adjunct professor at TBSI. Our supervisor, Mr. Zexin Fu, has also provided us many great suggestions. He is a great graduate student of Dr. Tan and does his research relating to the coherent cache and CPU design. So now, some basic information about ourselves. Ms. Liu Jierui majors in information engineering and shows great interest in the operating system and memory hierarchy. As for me, I'm an electronic and communication engineering student and find microelectronics and computer architecture intriguing. We are both so lucky to study in the City University of Hong Kong. To describe our project, we summarize it as a two-stage pipeline ORV32 for embedded low-power controllers. The simulator is derived from SPEC. This project provides the user with RISC-V unit tests supported by RISC-V tools. In addition, IMC extensions are available. Here comes the project directory structure. So the project mainly divides into 5 parts. The first part is the RTL code part. It contains the RTL description using the system Verilog code. And the second one is the single core ORV32 as is referring to the RISC-V golden model. And the third one and the fourth one are the multi-core ORV32S with cache coherency simulator with different protocols. And for the last one is the ORV32S unit test. We will update our current work now and clarify what we have done so far. So we have started our work in July and have been working on the project for the past 2 months. The block diagram of the microprocessor is shown below. In the first stage, the prefetch buffer fetches instruction from the instruction memory. And in the second stage, the decoder decodes the instruction and gets the opcode and the operands. Then the ALU will execute corresponding to the opcode, and finally store the result back to the GPR. Besides, the control and status registers are also implemented. We will explain the details in the following slides. Our first task at TBSI is to read the source codes and optimize the multiplier. Below is the schematic of the fast multiplier. So first, we break each 32-base operand into 2 16-base partial operands. Then do the 16-base multiplication one by one and then add them up. So for example, we break operand 1 into A and B, and break operand 2 into C and D. So during the first clock cycle, it computes A multiply C, and in other words, the low 16 base of operand 1 and multiplies operand 2. So we can get a 32-bit result, FE. And the low 16 base of the results in red is also the low 16 base of the final result. During the second clock cycle, it multiplies C and B to obtain HG, and then adds the result to the first cycle to obtain HI. Then in the third cycle, multiply D with A and add them up. And apply the same process to the fourth clock cycle, we can get the answer finally. Notice that now the low 32 bits are identical to the final answer. So if the instruction is MUL, we can obtain the answer directly without the fourth cycle. Although this method may increase the area and cost, it's worthwhile to do such an optimization since it decreases the clock cycles, which are used to obtain the answer significantly. After getting familiar with the source codes, we tried on the illegal instruction handling part. Once the illegal instruction is detected by the decoder, the exception handling process begins. First, the program counter of the instruction causing the exception is stored in the machine exception program counter. Then, the cause is stored in the machine cause register. And next, machine status, including the interrupt enable base, mode base, are renewed. Finally, it jumps to the machine trap vector and starts to process the exception. Once it finishes this process, program counter will jump back to the machine exception program counter and renew the status. Then the rest of the program will continue to execute. To support secure processing and contain faults, it's desirable to limit the physical address accessible by software running on the hard. RISC-V implements physical memory protection through configuring two kinds of registers, the configuration CSRs and the address registers. As you can see in the picture on the right, each configuration CSR is 8 bits, and the address register is 32 bits for RISC-32. A PMP entry consists of a configuration CSR and an address CSR. In RISC-32, 4 small configuration registers are combined into a big one, as shown on the right. Let's take a look at the configuration register in detail. In this layout diagram, the R, W, and X base are set indicates that the PMP entry permits read, write, and instruction execution respectively. When one of these bits is clear, the corresponding access tab is denied. The A file in a PMP entry's configuration register encodes 4 address matching modes of the associated PMP address register, which is off mode, TOR mode, and NA4 mode and NAPUT mode. NA4 is a special case of NAPUT, namely the natural aligned power of 2 region. When A equals to 0, this PMP entry is disabled and matches no addresses. When A equals 2 or 3, NAPUT ranges make use of the low order base of the associated address register to encode the size of the range, as shown in the figure in the lower right corner. When A equals to 4, TOR is selected. The associated address registers form the top of the address range, and the preceding PMP address register forms the bottom of the address range. And we have finished the PMP unit design, and the current work is to connect it to the processor. We also tested our project with various benchmarks such as Redstone and CloudMark. For Redstone, it runs 388 instructions within 427 clock cycles and scores 1.33 Redstone mini instructions per second. For CloudMark, it scores 1.9 CloudMark per million hertz. And we will test it using the new benchmark in Bench in the future. These data have shown how some of our implementations are verified through the in-bench tests. Next, my partner will show how the coherence is verified through the memory architecture, as these benchmarks follow certain memory coherence protocols.
Below is a call code which defines our memory hierarchy. In the RISC-V project, we adopt the L1 private L2 shared model. The call code builds up the processor data structure by piling up all the pipelines in the forms of strings. In the table, we can see what is the hardware feature of our memory design. The L1 data cache has a capacity of 32 kilobytes, whereas we have 1,024 cache lines. Each has a capacity of 32 bytes. The mapping method in our model is direct map. Now, between the hardware feature and the software call code arises a problem. How do we describe the buffer size, for example, the store buffer? The physical attributes are out of the clock verification concern and is our next major change in the memory model definition. So, let's look at the memory models. The total store order, typically for x86, and weak memory model, typically for ARM, are both adopted in RISC-V design, known as RVTSO and RVWMO. There is a non-deterministic total order on all memory operations. For RVTSO, the order excludes the store-to-load ordering, different from sequential consistency. As for RVWMO, the order follows 13 specific instructions indicated in the graph on the right corner of the above. In our project, we now focus on realizing the total store order memory model, which is harder for the implementers, but has higher performance. And this model can be described by the tso.cat file. And finally, we come to the verification steps. We have learned from the CCI Check project, whose details can be found through the link below. Thanks to America, we obtained the algorithm which draws a directed graph as a visual aid for coherence verification. In such an algorithm, the microarchitecture is defined as the collection of locations, legal paths, performance, and guarantees. The actions the microarchitecture took is described in the directed graph known as microarchitecturally happens before. And there are three kinds of edges in the graph. The static edges, which are generated by the instructions themselves. The observed edges, which are observed in a particular execution, including race from, write serialization, and from rate. And finally, the preserved program order, which defines the set of reorderings guaranteed by the architecture or not to occur based on the types of the access. All in all, the verification can be illustrated through such a graph. The HERT tool is used here to provide a self-designed memory model verification suite. It can accept the litmus test, which is a small parallel program designed to exercise the memory model and produce certain results. The result is then analyzed by the CCI check through the interface. The CCI check calc code enumerates the edges until a cycle appears. According to early detection of cycles, unsatisfiability of constraints, and depth-first algorithm, the CCI check has the pruning and scalability feature. Our next step to take is the relaxed concurrency model. We adopt a specific language called SAIL, whose user manual can be found through the link. SAIL is a language for describing the instruction set architecture semantics of processors. SAIL aims to provide an engineer-friendly, vendor protocol-like language for describing instruction semantics. And essentially, it is a first-order imperative language, but with lightweight dependent typing for numeric types and bit vector lengths. Now, as we have mentioned in our explanation of our work, certain obstacles have arisen, such as the difficulty to describe the hardware feature in our algorithm. We have set clear objects for our work ahead of us. Generally speaking, our tasks are practical and meaningful. This summer, we have been doing the project on Dr. Tang's guide and Dr. Ray's advice. The courses we have taken at CDU offer precious knowledge for the RISC-V related work. For example, the doctorate teaches the course EE4204, Digital System Design VHDL. In the course, we learn to deal with memory access handlers such as the direct memory access. In addition, the advisor and supervisor from the RIOS laboratory also supply us with abundant experience and information. The prompt reply to our questions and clear goals helped us to approach the target better. This is the end of our presentation. We're so grateful for your patience and support. Thank you, everyone. Please feel free to propose any questions.
Hi, Jerry. Great presentation. I have a question. How fast does model checking run? What's the runtime?
Currently, we've tested it just simply on the x86 TSO models because for RISC-V, there are some litmus tests still need to be written, but the graph can be generated very fast, like in seconds. I think 1 or 2 seconds.
So you're saying runtime is seconds, right?
Yeah, sure.
Okay.
But the problem is currently the litmus tests are only contain like several instructions. So if it is for more instructions, it might just take more time.
Okay.
Yeah, Dr. Tang, we hope to arrange more students, to work together along this line. Thank you for that.
Thank you, Dr. Ray. Thank you, Vince and Carrie.